All right, thank you everyone for sticking it out and being here this morning. I'm going to switch gears a little bit and talk about extratropical cyclones in Europe and the impacts that we see there. First, I want to make a disclaimer. I didn't actually participate in this research. I'm actually presenting this on behalf of my European colleagues who could not attend the meeting today. I'd also like to acknowledge a couple of our partners on this project at ETH, Zurich, and the University of Bern in Switzerland. They were heavily involved in the hazard set development for this risk assessment model. So why are we even concerned with European winter storms? Well, over the last several decades, they have caused roughly $90 billion in damage. And of the top 25 insured loss events worldwide, 4 of these events have been from winter storm events, and the most costly being that of Daria in 1990. So when we think about risk assessment modeling, we want to understand what the hazard characteristics are, what's the probability of occurrence, how intense is it going to be, where is it going to occur, what's the spatial extent of that hazard. And then we want to understand the relationship of the hazard characteristics with respect to the built environment in the populated areas, which is our value distribution. Also, we want to dive down a bit deeper and understand the specific construction types or the different types of buildings, hospitals, schools, residential buildings. All of these different types of construction have different vulnerability characteristics to a variety of hazards. For example, a wood frame building would perform differently in a high wind event than, say, a reinforced concrete building. And so we want to make sure that we characterize that in a risk assessment model. Finally, the economics come into play. We want to understand the value of the structure, the value of the contents. And if it's a commercial or industrial building, what's the value of the business if there happens to be an interruption of that business for a prolonged period of time? So for this talk, I'm largely going to focus on the hazard characteristics and how we developed the hazard set we used in our Winter Storm Europe risk assessment model. This is the process that we used to develop this hazard set, and I'm going to focus or look at this in 2 different ways. The first is the event identification. We want to have an understanding of what the historical events were, develop a climatological perspective of those events, and then use that for our hazard model, where we develop a simulated event set so we can develop probabilities of risk for any given location within the European region. So the basis of our hazard set was the 20th century Reanalysis data sets. Now there are roughly about a dozen different Reanalysis data sets out there that cover the entire globe. However, this one extends the furthest back into history, beginning in 1871, and we used it up until 2010, but I believe it extends to 2011 or 2012 now. So it's long. It provides a consistent representation of the weather conditions at any given moment in time, and but it's also only one representation of what that actual historical weather condition was like. And it's also global, so it provides us a way to replicate this methodology elsewhere if we need to. So for the event identification, as I mentioned, we use the 20CR data set, which is available on 6 hourly snapshots on a 2 by 2 kilometer grid, or 2 by 2 degree grid, I'm sorry. And we focus largely on the wind and the surface pressure data from this data set. To track the events, we looked at it from two different perspectives. We wanted to look at the extratropical cyclones themselves from the sea level pressure, and we used a methodology by Zimmerli and Schwartz to do that. And we wanted to also track the high wind speed footprints of each of these tropical cyclones, because usually it's asymmetric in terms of the winds. The highest wind speeds tend to be on one side of the storm and not necessarily around the entire pressure center. So we wanted to track that wind footprint in addition to the central pressure of the tropical or the extratropical cyclone. Excuse me. And then from this, we end up with our historical event set, and you can see the time series of events that have occurred over the last roughly century and a half from this 20 CR data set. And on average, you see roughly about around 10 events per year. Developing the hazard set this way also enables us to take a look at some of these historical events that have happened that we've kind of forgotten about. They're really strong events, but they may not have caused a whole lot of damage, or there's no longer any living population that remembers the occurrence of this event. And this is a particular case, I believe, before 1900, and this is the modeled footprint of that area that was affected, with the warmer colors being the higher wind speeds. And if this event had reoccurred today, we could see up to $50 billion in loss. Now, the 20 CR data set provided a way for us to develop the original historical event set. However, to define the impacts at particular locations and better understand the intensity of the storms, we needed to do some downscaling. 2 degrees by 2 degrees just simply wasn't good enough resolution for us to come up with reasonable estimates of the intensity. So we used a multilinear regression technique to downscale the 20 CR utilizing a regional climate model from the ENSEMBLES project sponsored by the EU. This brought us down to a resolution of 25 kilometers, which helped better define the hazard characteristics along the coastlines and to some extent in topography, but it still wasn't quite good enough for what we needed. So we used a distance-weighted average to extend that resolution down to roughly 10 kilometers. Now, the grid that we use, or the calculation units that we have defined here, is an irregular grid, and you have a higher density of points in higher populated areas. Now, in terms of the hazard model, we take each of the historical events that have occurred, and we use a random walk evolution process, both on the original track, which is based on the wind footprint, and then the intensity evolution, which is based on the central pressure of the extratropical cyclone. And so we take the climatological characteristics of the particular historical track, and we use the probability distributions and the statistics around that to evolve the track intensity and propagation. And by doing that, that enables us to create simulated events or potential scenarios that could have happened, and the resultant costs and impact from these different scenarios. Excuse me, my voice seems to be failing a little bit here. So what this enables us to do is to create unprecedented events that haven't happened before, but yet they're still climatologically representative of what could happen. So for example, let's take a look at the historical Daria event This is the most costly winter storm event that has occurred in 1990. And you can see the historical footprint on the left-hand side. On the right-hand side, you can see a variety of different simulated or probabilistic Darias. So slightly different scenarios of the original Daria event. And you can see in this plot here that the wind speeds are much higher. The impacts would be greater in this particular scenario. Whereas in this scenario here, the wind speeds are less even though the storm follows a similar track. And so the impacts we would expect to be less from that particular scenario. I should mention that for this particular case, for Daria, we ended up having about 69 different scenarios that were developed for this case. And it's similar for each of the historical events that we observed from the 20 CR data set. So now let's talk a little bit about validation. We want to make sure that the simulated events still match up with historical observations. And in this case, on the left-hand side, you can see the different observation stations across northern Europe, and the colors represent the observed wind speeds. On the right-hand side, you can see the footprint of our calculation units and the representative wind speed that was modeled. And in general, the footprint matches up fairly well. Now this, the performance of the model worked fairly well for the majority of events. However, there was roughly about 3% of the simulated events and historical events that did not quite work very well using the process that we had. Now these events were a little bit unique in that they either intensified very rapidly, so within that 6-hour window of the 20 CR data set, and that wasn't captured by the 20 CR, or they were very small spatially. And so they were difficult to interpret and then simulate additional scenarios. And Lothar in 1999 was actually one of these specific cases. And so what we had to do was an additional adjustment for these small-scale systems that were very intense. And after that adjustment, we had a much better representation of the wind field for those particular storms. For further validation, we looked at specific observation stations and the observed gusts for the different events. And this is just a scatter plot showing the observation versus the simulated gust speed at each of these locations for each of the historical events. And you can see in general, they all match up pretty well. We do tend to see an underestimation of higher wind gusts, and this is kind of to be expected though. Because we're using reanalysis data, the turbulence parameterization schemes or the resolution of the model does not enable the ability to accurately model higher wind speeds and gusts. It's simply a nature of the models. So we have to take that into account. And I am running out of time. All right, so let me speed up here. We do have one exception in complex terrain. It still does not work out very well, but we do have lower population in those areas, so it's less of a concern for us. And I'll skip on through this and just close by saying that in the end, we develop a scientifically, physically representative and statistically representative event set that we can use for risk assessment modeling for Europe for these events in the future. So,
Thank you very much, Kirsten. Again,